All right, another problem. Jordan throws a ball upwards from ground level with a speed of 20.0 meters per second. When is the ball 5.00 meters high, and how fast is it moving at that point? For some reason, that is in quotes. We'll see why shortly. And then we actually have a follow-up question. How high does the ball get? Well, in other words, you throw a ball upward. What's the highest point? How high does it get? I guess that's what this is asking. So let's, again, what do? We read the problem. Let's draw a diagram. What's going on in this case? We have Jorn here throwing a ball. Now, this problem could have stayed, oh, it actually tells us here, sorry. The ball is thrown from ground level, so apparently Jorn is reaching down and throwing the ball upward from ground level. So we can draw Jorn holding the ball here at ground level. Throws it upward, so it's going straight up in this case, with a speed of 20 meters per second. Okay, so we're starting out here at 20 meters per second. When is the ball 5 meters high? So the question is, at some height of 5 meters, how fast is it moving at that point? And then, how high does the ball get? All right, there we go. So there's a drawing of our problem. What are we going to do? We define our coordinate system. Now, our one-dimensional motion is not a horizontal motion. It's a vertical motion. But that's okay. Vertical motion is still one dimension. So we've got a ball starting at the ground and going upward. So why don't we define the ground as our origin? And the ball is going upward, so we'll define upward as positive. So here's our coordinate. There's 0 and upward as positive. Here we go. There's our coordinate system. Write down our variables. All right, let's do that. Now, sometimes some people, if they've got a vertical problem, they like to write down their variables as y instead of x. But totally independent. It doesn't matter. You can do that if you want. All of our equations are written in terms of x, so I'm just going to use x. So let's write down our variables. X naught, x, v naught, v, a, t. There we go. So here's our problem. The ball is being thrown upward, and we are being asked when is the ball at a height of 5 meters. So what do we have? X naught. Here's the initial position. Let's remember, initial and final. So here's initial, here's final. What's the initial position? X equals, or what's the initial height, you might say? X equals 0. X naught equals 0. Final height? Well, actually, in this case, we know x. The final height is 5 meters. V naught, what's the speed initially? We're told 20 meters per second. Final speed, what's the speed up here? Well, we have no idea. We don't know what the ball is doing up at that point, so we don't know v. A, what's the acceleration? Anytime an object is moving only under the influence of gravity, which is what this ball is doing. This problem did not say so, but anytime we have a problem like this, even if it doesn't say it, we're going to ignore air resistance. The problem really should state that to be precise, but if it doesn't, we're just going to ignore it. Involving air resistance is a much more difficult problem, which we'll not do at this point. Okay, so acceleration. What's the acceleration? It's going to be the acceleration due to gravity, which is 9.80 meters per second squared. But remember, the acceleration is downward. We defined upward as positive, so what is downward if upward is positive? Downward is negative. So our acceleration is negative 9.80 meters per second squared. That's very, very important. You've got to make sure that you remember that negative sign in this sort of problem. If your upward is defined as positive, then the acceleration, which is downward, has got to be negative. There we go. And t, do we know t? We do not. We do not know what t is. There's nowhere in the problem that tells us how much time this takes. All right, there we go. Now, what are we looking for? How fast is it moving at that point? That point. in quotes for some reason. In other words, at 5 meters. So what are we looking for? How fast is it moving? When the ball is at 5 meters high, with a speed of, I'm sorry, I wasn't reading that correctly. When is the ball 5 meters high? So when is the ball? We're looking for t. And how fast is it moving at that point? So we're looking for v. This other one, how high does the ball get? Well, that's a very different question. That's asking about what's the maximum height that the ball gets. So in this case, we're tossing a ball up, and then at some point 5 meters high, it's going to pass that point. But that's not the same as the highest point that it can get. So these are two separate problems. We're going to have to solve these separately. We'll solve the first part first, and then we'll come back and we'll take a look at this one. All right, so let's remember, we've got to come back and solve the second part after we finish the first one. So let's take the problem down, put the equations up, and go through it. Okay, here are the equations. What are we going to solve for first, v or t? Just let's solve, in this case, let's solve for t first. There's something that I want us to see before we go ahead and solve for v. So how can we solve for t? Could we use the first equation? We cannot because we don't know v. Can we use the second equation? Again, no, because we do not know v. Third equation? Yes, we could. It's got a t in it, and we know everything else, so we could use the third equation. Fourth equation? Again, no, because we do not know v. So let's use the third equation and see if we can't solve for t there. Again, let's come over here. What do we know? X naught is 0, so I'm just going to say X naught is 0. We can ignore that. V naught is not 0, A is not 0. Okay, so X. Let's put some numbers in. X. X is 5 meters. So 5 meters equals V naught. V naught is 20 meters per second times t plus 1/2 times A. A is negative 9.80 meters per second squared, and then times t squared. All right, there we go. There's our equation, and we need to solve that for t. Ooh, that's a little tricky. What we need to do, well, let me ask you, how are we going to solve this? We've got a t and a t squared and a constant term. We have to solve this using the quadratic equation. Let's put this into standard quadratic equation form, which with the variable t, it would be a t squared, a is a constant, not the acceleration, a t squared, or just think of it, ax squared plus bx plus c equals 0. So in this case, it'll be a t squared plus bt plus c equals 0. This coefficient of t squared with the minus sign here is going to be negative. So what I'm going to do is bring this to the other side just so that constant in front of the t squared is positive. You can leave it over here and take everything over here. I usually like to make my initial constant in front of the t squared term positive just because I think it's easier. I don't lose as many negative signs in my solution. Again, 1/2 times 9.8, that's 4.9. And the negative over here will make it positive, so I get 4.90 meters per second squared, t squared. And then bringing this over to the other side, minus 20 meters per second t. And then I'll have a plus 5 meters, and then all of that will equal 0. Now, how are we going to solve this? Remember the quadratic equation. If this is the constant a, now be careful, it's not the acceleration a, it's the quadratic equation a. So that's a, this is b, this is c. In this case, remember, what's the solution? T equals the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. That is an equation that I think you should be familiar with, and I will expect you to remember that. So if you don't remember that equation, if you haven't memorized that, you better make sure to get it memorized fairly soon, because that's the sort of thing I will not give you on an exam. Now you do get a card that you can put things on, and you would need to put it on that card if you don't remember it. Okay, let's stick our numbers in. What do we have? We have t equals negative b. So here's b. So that's a positive. Negative of a negative is positive 20.0 meters per second, plus or minus square root of b squared. So that's negative 20 squared, but negative squared is a positive, so I'm just going to drop that negative sign because it's squared and it's going to be positive anyways. So 20.0 meters per second, quantity squared, minus 4 times a, 4.90 meters per second squared, times c, which is 5 meters. All of that square root. And then this whole thing under 2a. Now, what I'm actually going to do, I'm going to separate this into two parts. I'm going to put this under 2a, which is 2 times 4.90 meters per second squared. And then I'm going to put this under the 2 times 4.90 meters per second squared. And I'll explain why I do that in just a second. Then I'm going to solve this in two parts. I'm going to say t equals this part plus or minus this part. So I'm going to solve them separately. And what do we get? We get 2.04 meters per second divided by meters per second squared. Now here's one of those problems that I just talked about with multiple numerators and denominators. Let's think about this. We've got meters per second, and then we're dividing by meters per second squared. If you divide by something, it's like multiplying by the inverse. So I'm going to multiply by seconds squared over meters. The meters cancel, one of the seconds cancels, and we're left with seconds. So t is equal to 2.04 seconds. Well, that's good. Seconds for time. Plus or minus. And then do all of this out. And in that case, we get 1.78. 1.78. And, oh, good grief, look at this. We've got meters per second squared. So meters squared per second squared. Meters squared per second squared. So these will be meters squared per second squared. Square root will be meters per second. And then divided by meters per second squared. Well, that's exactly what we had over here. So again, we'll end up with seconds. So that's good. Seconds. Now, we've got two possible solutions here. We can add or subtract. If we add them, we get 3.82 seconds. And if we subtract them, we get 0.26 seconds. Okay, this is funny. We've actually gotten two solutions to this problem. Why do we have two answers? This is why the question said in that point, where that was in quotation marks. Because there are two times when the ball is at 5 meters. Now that makes sense, actually. As the ball is going up, it passes the 5 meter mark. It goes past, and then it passes the 5 meter mark on the way back down. So it makes complete sense, complete physical sense, that we actually have two possible times for the ball to satisfy the conditions. In other words, to be at a height of 5 meters. Now let's just think about this for a second. We've got one small time. What's that correspond to? Well, that must correspond to the time when it passes going up, which will be sooner. It then goes all the way up, comes back down much later, more time later, and so we have a much larger time for the second passing as it passes back down. Very good. So we've got two different times. Well, what about the velocity? What are the velocities? Well, if we've got two different times, let's see what happens. How are we going to solve for v? Well, can we use the first equation to solve for v? Well, yes we could. We've got v naught, we've got a, we've got two possible times. We could use the first equation. Could we use the second equation? Again, we could. This would be a little bit more difficult to shift quantities around, but we could. Third equation? No, it does not have a v in it. Fourth equation? Yes, we could. We could do that. Let's use the first one. It's It's very straightforward, v equals v naught plus at. Now, the fact is that if we use the fourth equation, we could solve that without using our calculated value for t. So by rights, like I said before, you might want to use 4 to solve it so that you wouldn't compound your mistake. But I actually want to use the first one because it will tell us the corresponding velocity for the two different times, and I want us to understand that. So let's use the first one. What do we get? We get v is equal to v naught, which is 20 meters per second, plus a is negative, so I'm going to write minus 9.80 meters per second squared, times t, and then we can put in both of these values. We can put in 0.26 seconds and get a value for v, and then we can put in 3.82 seconds and get a value for v. Now, what values of v do we get for those corresponding times? Well, what we get is, for the larger value, we get negative 17.4 meters per second. For the for the smaller value, we get positive 17.4 meters per second. Very, very interesting. Does that make sense? Yeah, I think it does, just like we were saying. For the ball going up at 0.26 seconds, what's it doing? It's going up, which is what kind of a velocity? Upward. If upward is positive, it's going to be a positive velocity. The shorter time gives us a positive velocity. But what about the later time? What's it doing? It's coming back down. It's coming back down, and so what do we get? We get a negative velocity. Very, very good. That makes perfect sense. Getting two answers makes sense, and then getting these two different values for the velocity makes sense. One of them going up, one of them going down. Before we move on, so before we go to that other part of the question, I want us to just think about this. Look at the times. Where did these come from? They came from 2.04 seconds plus or minus 1.78 seconds. What do these two times mean? They came from our quadratic equation solution here. But what do they physically mean? What are they physically, what are they physically telling us? Let's think about this. What does the motion look like? It's going up and then coming back down. And what we're saying is the time here is, one of them is this minus that, while the time here is this plus that. So can you think of what those two times might mean? What happens at 2.04 seconds? Well, as a matter of fact, what happens at 2.04 seconds is when the ball is at its, can you see? I hope you can see. At the maximum height. It takes 2.04 seconds for the ball to get it to its maximum height. And then 1.78 seconds later, it's back down at the 5 meters. Or 1.78 seconds before it got to its maximum height, it's also at 5 meters. This is very interesting. The time that it takes to go from the, okay, so it takes, here we go. So it takes 0.26 seconds to get up to 5 meters. But 2.04 seconds to get up to its maximum height. It passes the first time going up at 1.78 seconds before that, and then it passes it again on the way back down 1.78 seconds after that. So 2.04 plus and minus 1.78 seconds. The motion is symmetric. The amount of time that it takes going up from 5 to the peak is the same as the amount of time it takes to go from the peak back down to 5. The motion is symmetric. Very, very good. We might not have understood that if we hadn't done the quadratic out in these two parts to see what these mean. Very, very good. Okay, let's go on to that last part of the problem. Let's keep these in mind. Let me write these down. I'm going to write down this whole part. 2.04 seconds plus or minus 1.78 seconds, which leaves us with 3.82 seconds and 0.26 seconds. And then the velocity, what we found was plus or minus 17.4 meters per second. There we go. All right, let's go back to that second part of the question. Let's see what that is.